This video is in continuation to our previous video on the same topic. The previous video talked about the theory aspects, and in this video, we perform the hands-on. Putting them together completes your learning path. As you know, in all our hands-on videos, we walk you through every single line of code. Let's get started. All right, so we are at the Google Collaboratory one more time, and I've already pointed to the data source, which is a very popular Wisconsin cancer data set that's available at UCI Machine Learning Repository, a very popular source for data sets which have been used for research purposes. So I'll provide you a link for that as well. You can always access that data set. Now, let's start working on the data. So we begin by calling the basic libraries, NumPy, Pandas, Matplotlib, and Seaborn, and this is where we are. So these libraries have been imported. We begin by reading the specific data set using the pandas read CSV method, and we are storing it by the name of df, in short for data frame. We can check how big this data is. We can always do df.shape, which tells us rows and columns. So we seem to have 569 rows and 32 columns. Essentially, the features in this data set are the outcome of a specific test for cancer, which is known as the FNAC test, fine needle aspiration test. Let's check the first few observations of the data set to get a better idea about how the variables are. So it doesn't give the names of the variables, but if you check the source, that is the UCI repository, it has the proper names of each of these variables. So right now it shows the variables are from V1 to V32. Like I said, since we have the names of the actual features available, and this is the mapping of the features, so we've created a dictionary where this is the key and this is the value. These are the actual features available on that page. And we are using a rename method on the pandas data frame to apply this mapping. What is this mapping? This mapping is in the form of a key value pair or a dictionary format. And we are applying this in place, which means these changes will be effective on the data frame. So let's do that. This will make the variables more relatable and might give a little more meaning to the variables, though we don't become a domain expert by just doing that. But let's try to check the head again after renaming the features. So one thing you see clearly is that first feature we would have otherwise understood as some number which has a meaning is just a patient ID. And the second feature here is the diagnosis. Now, this is the dependent feature. So originally this data was used to predict the cancer, whether the outcome of the test was malignant, which is confirming a cancer, or benign. And using these features here, we were supposed to predict the diagnosis. But for our exercise right now, we are only going to concentrate on the multicollinearity. We are not predicting the outcome. So we will drop the features like ID and diagnosis. We don't need these. ID is as such a nominal variable, doesn't have to do with cancer as such. And diagnosis is not our focus because we are trying to eliminate the correlations between the independent features. So we are dropping these two features in place using df.drop. Now we're talking about two approaches. First is that we can remove one correlated feature from each correlated pair. Before we do that, let's just look at what's the state of current correlations in the data. So we can do this using a heat map. We've just adjusted a figure size and we can try multiple sizes, whatever works best, we can go for that. And using a heat map to which we are passing a correlation matrix, df.cor. That's the way to call it. And we are choosing a color map, which essentially is going to show us the shades of reds and blues. We have mentioned that the range of correlations will be anywhere between -1 to 1. If you know correlations, you know this is a value which always ranges between -1 to 1. Let's visualize this. So we started with 32 features. We have dropped 2 features. Right now, we are looking at 30 features. Now, if you're looking at 7, 8 features, you can always do something that's known as the annotation here, and you will be able to read the values of the correlations itself. But when you have too many features, it may be a lot of clutter to print the values on top of this heat map. So what we are doing instead is we are trying to figure out how many correlated features are there. Because even if we start manually counting and if the values were here, there's a high likelihood that we make a mistake in counting. These are not limited features. These are decent amount of features. So we will be writing a function finding out the correlations which are greater than a threshold. This is where we've mentioned it's very important. So we're writing a function which is known as correlated feature pairs. You can give any name. This is our choice, which takes an input as the data set and a threshold that you want to check for. We are creating an empty list, which will be storing some correlated pairs after some time. And we are generating the correlation matrix on the data set, which has been passed as an input. We are applying the correlation matrix. Now, we are iterating over this correlation matrix using 2 loops. First is a loop that's going to go over all the columns starting from the index 0 to the last column in the data. And the second for loop here, which is a nested for loop, is going to go over all the values starting from 0 up to the ith value here. Finally, we will be looking at the absolute value of the correlations at the index I, j, which is greater than threshold. If we find it, we will store it for feature 1 as column I, for feature 2 as column j from the same correlation matrix. So we will get to know which is the feature 1 and which is the feature 2. And finally, we append it to the list of correlated pairs in the form of a tuple. So feature 1 and feature 2 pair would be an element of this list. And we are returning the correlated pairs. This is where we have set a correlation threshold, let's say 0.9. And at this point, we are applying this function that we just discussed, which seeks two inputs, the data frame, which is our actual data frame that we read, and the correlation threshold, which we just decided here as 0.9. We can always change this and look at different correlation outcomes. What we are checking after that is we are printing an outcome which is going to suggest how many correlated pairs were found. So this is a string. It will say total and whatever will be the length of the correlated pairs. Correlated pairs is basically a list. So the length of the list will tell you how many elements are there. And what are the elements of that list? Just the correlated pairs. So it's going to count the total number of correlated pairs that it finds. Then we are getting inside the correlated pairs and printing those pairs like this. So it will say feature 1 and feature 2. Let me run this. And then you can appreciate the output. So it says 21 correlated features found. And which are these correlated features? These are the names of the correlated features. These are 21 pairs that it has found. Now, let's say you decide that of all these correlated pairs, you simply want to drop the first feature. We discussed that as the first approach, that if you have correlated pairs, you can keep one feature and drop the other. So for that, we are again writing a similar function, but it has a little different usage. So we are writing another function, which is called correlation detection. Again, the name is not important. It's a user-defined name, which takes the input as the dataset and threshold like the previous function. But for the features, we are using a set form. Why? If you see this outcome here, you'll see a lot of first variable names repeated. For example, area worst, if you see, this is something that appears 5 times. Perimeter worst, this appears 4 times. When you create a set, it will always store the unique entries. That's about the basic data structures in Python. List can store repeated entries, but set would only store unique entries. We want to be eliminating these features, so we would need their unique names. Again, we are creating an empty list called correlated pairs. We are calculating the correlations and storing them as correlation matrix. 2 for loops like the previous stage, exactly the same approach. We are looking at absolute values of correlation which exceed the threshold, and we can set this threshold once again to 0.9. From the correlation matrix, we are taking the name of the feature which is found to be correlated, the first feature, and then we are adding it to our set. So notice for the list, we used append method. For a set, we are using the add method. This would return a set which will have unique entries of those features which have been found in correlated pairs. So we have taken the first feature of the 2 paired features which are correlated. Let me run this. This is just a function definition. Now to apply this, we are first making a copy of the data frame because we don't want to change the actual data. We are making a copy of the data frame, which is called df1, a copy of the original df. And here we are applying that function. Which function? The function that we just discussed here, which takes the input as the data frame and the threshold, which we have passed as 0.9. And now we are checking how many features are there in the set, which we are going to eliminate. So it says 10 features. Can we count this here? So this is 1, this is 2, this is repeated, so we'll not count it again. 3, 4, 5, again repeated, will not count. 6, 7, 8, will not count the rest. 9, and 10. So there are 10 features that we saw here, which we have detected. You may be wondering, we could have easily counted it here. This may be easier for now, but what if you're dealing with 150 features? You'll not be counting it manually, right? So it's better to write functions which would do your job accurately. Now let's check what are these correlated features. So these are the same 10 features that we just counted above. And now it's simple. We just have to do another df1.drop. Just pass the set. 2x is equal to 1. It simply means that we are dropping these columns. Which columns? Columns represented by this set. And in place is equal to true. So now let me scroll up and check the shape of the data frame again. Shape 1 means columns. So we are left with 20 columns now. So we started with 32 columns, dropped the ID and the diagnosis, left with 30 features. Of the 30 numerical features, independent features, we have dropped 10 features. We are left with 20 features. If we now check the correlation matrix again through the heat map, let's see how does it look like. So it again may not be very clear, and a couple of places you may feel that there are still some strong correlations. And we are not annotating here to read these, but can we apply the same function that we wrote earlier, which actually detects the correlated pairs, and see if in this data frame, df1, now we have any pair which is correlated. We are writing the same function, takes the input as the data frame and the correlation threshold, and we are printing if we still have any such pair. And what does it say? Total 0 correlated pairs found, which means we have eliminated all the features which have correlations values greater than 0.9. Now let's move to the second approach, which is VIF. Now VIF as a concept has already been explained as a part of theory, but here we'll be directly using VIF through a library called stats model. Let's make a copy of the data frame because this is a different treatment. So we need to make another copy of the original data frame. And from the stats model, stats outliers influence, we are calling the class called variance inflation factor. Here, we are trying to create a nice data frame, which is an empty data frame. It has one column which stores the feature names of the original data that we copied, and another column which will store the VIF values. Now, VIF is something for which we don't have to write a function. We will just use the existing function that's available through this class. So what we are saying is that for each I in the range of the data frame columns, df2.columns basically means all the features which are present in the data frame 2, which is a copy of the original data. So we are going over each feature, and to the VIF or variance inflation factor, we are passing the values within the data frame along with the column name. And this is the only input that this function, which is a ready-to-use function, needs. Finally, it will give us a data frame which will have 2 columns, name of the feature and its VIF value. And we are printing VIF values, sorting it by VIF in a descending way. Ascending is equal to false means in a descending way. So we'll get to know which feature has the highest VIF value. Let's run this. So see, VIF values are really alarming here. And these are starting from 63,000 something to 24. So that way, if you see, for all these 30 features, the VIF values are much greater than 5 or 10, which is a typical threshold. Based on VIF, we drop the features one at a time. So we'll be dropping the one with the highest VIF value first, and we have to do it recursively. It's a common mistake. A lot of times people would detect VIF and they'll drop all the values which are greater than 5 or 10 or the chosen threshold at once. That's not how it is supposed to be. When you drop one VIF value, the highest VIF value, the entire VIF calculation is revisited. So a lot of changes will happen here. This way, if you see, if we drop all, we'll not be left with any feature. Then there's no point doing VIF, right? So we'll do VIF in a proper way. For that, here is a small piece of code. We have chosen the threshold for VIF as 10, which means we are trying to eliminate those features, which when explained by other independent features, have an R square of 90% or more. So we have set a flag here, which is set to true. Why have we done this? We are going to eliminate the features one at a time, and we don't know how many times we are going to run it. So in such cases, you will not use a for loop. For loop is a loop which goes from one end to the other end. In cases where you don't know how many exact iterations you need, you will be using a while loop till you reach a point where there is no feature with a VIF greater than 10. So you want to terminate this loop at that stage. So we are setting the while loop to begin with as true. We are creating the same data frame that we talked about. We are putting it through a loop now. The same thing that we discussed a couple of lines above. We are putting this just through a loop. So in this particular case, we are checking for every feature whether its VIF value is greater than max VIF. What is max VIF? This is our threshold here that we have set. If the VIF value of the feature is greater than the max VIF, we are dropping that specific feature. Axis is equal to 1 refers to the column. And then we are also printing a message which says remove variable with high VIF. We are mentioning the name of the variable and also the VIF value that this feature had. But if the feature does not have a VIF greater than the maximum value permissible or threshold, we are setting the remove flag to false. Now, the moment this is set to false, this while loop will stop execution, which means you've reached a stage where no feature has a VIF greater than threshold. So let's run this. And now, after executing this, let's just try to read the message. There are many features which seem to have been dropped. And every time, because we are printing the message, it continues to drop them iteratively. But has it dropped all the features, all the original features? Of course not. We'll have to check. It has only dropped the features which have a VIF greater than the threshold. And if you see, the VIF values seem to be recomputed. In our original output, if you see, the lowest VIF value was 24. But if you can see here, we've dropped features with VIF up to 11.17. Where would this have come from? This would have come because the VIF values were recomputed. Let's check what's the shape of the data frame now. So now you see you're left with only 7 features. We started with 32 features, dropped the ID and diagnosis column. Those were not required. We were left with 30 features when we started VIF. And out of 30, 23 features have been dropped. So this is a very powerful technique which has eliminated 23 features out of 30. And now if we try to look at the heat map, because we're left with only 7 columns, we can also afford to do the annotation with 2 decimal places display. Let's see how our heat map looks like. Here is the heat map. So now if you see, there is no pair of correlations which is to the north of 0.9 or even close. All the features that we have do not seem to have correlations. By the way, correlation matrix is always symmetric. So if we read the value, the lower triangle or the upper triangle, that's one and the same. We don't have anything which is significant here. So VIF has done its job pretty well. In case we want to check if there's anything that's still left and using the earlier function, the first function we defined here, this time passing the input as data frame 2 and the correlation threshold, which is 0.9, it'll again say 0 correlated pairs found. Right. So we've covered 2 important techniques relative to correlations. First one is to drop the features. Second is to apply VIF. PCA has already been covered in a detailed set of videos. A collection of about 4 videos on PCA alone exists that you may refer to. And Ridge and Lasso have also been covered separately. All the links are available in the description. If you're interested in learning these techniques a little better, you can always do that. Hope this video helps you get better understanding of multicollinearity treatment. Thank you.